it's quite important that you really get comfortable with the difference between your normal equations that you've been solving for years and trig equations. So we're doing another step through here to have a look at how do we solve a trig equation and why do we have to do it differently. So we're going to start off with trig equations, but looking now at the background in a little way. So our beautiful trig graphs. Promise you these are beautiful. You can use your vivid imaginations this morning because my graphs seem to be even worse than usual. Okay, so you should now be familiar with the fact that sine looks something like this, and it goes on in both directions. Cos, let's extend a little bit, is going to look like this, going on and on. And tan then is our one who looks something slightly different. Okay, so we have y and x, because we're good students and we label at least our axes, so we're not going to put numbers on these ones. Okay, so we have y equals sine x, y equals cos x, and y equals tan x. And even something like this is a bit dodgy, the top of this sign. It should be more symmetrical, and you'll see why just now. Okay, so just bear it in mind that I would have paused before giving myself full marks for that one. So what we're looking at here is, let's say we have an equation, let's say half equals sine x, or third equals cos x, or minus 2 equals tan x. Okay, back to way back when in IG, when you thought about the idea of solving graphs, solving equations graphically, getting things back to front today. So if you said, okay, y equals a half, there's y equals a half. Okay, y equals minus a half would come down here. Y equals 4, we can only do on tan because of course sine and cos don't go up that high. Okay, so here we have now some equations to solve, and those equations, the answers would be at our points of intersection. So in each case here, we have more than one answer to the equation. And of course, if we extended our graphs out even further, we'd have more and more and more solutions to our equations. But that's a bit of a problem because our calculator is designed to give us one answer or two, depending on how we plug things in. So if we plug in positive and negative values, we can get two different answers, but who says it's the answer that we want? So what we need is a way to get an answer that we trust and then use that to get answers that we want. So what are we looking at? We're looking at the periodicity of these graphs. Okay? Because it's repeatable. It's the same thing over and over and over again. So if you have something that repeats like that over and over and over again, then you can predict. And when you can predict an answer, then you can go from one answer and you can calculate all sorts of other answers. So we have a predictable relationship between our answers. So what we're going to do is we're going to understand that first 360 degrees, the first 2 pi radians, and then we are going to predict our answers from there. So we're aiming for full understanding of the first, but here's the catch. It's not always 360. Remember, tan is a period of only 180. And when we play with our transformed graphs, then sometimes the period even for sine and cos would be 180. Sometimes the period would be 720, depending on how we're transforming it. So we're aiming for full understanding of the first period. That is then a word that we can apply across all 3 functions, across all the different situations. So if we understand that first full period, then we can start to make predictions outside of there. And that's how we get into our cast. So we're going to recap that cast a bit from the other day. Okay, so I've just been asked a question of, does a period mean the first 180 degrees? And now I have the wonderful ability to go backwards and forwards in my whiteboards. So a period is one repeat of the graph. It can be 180, it can be 360, it can be 720. It depends on the precise graph that you're looking at. So in this case, what we've got here, with our basic sine, cos, and tan, our period for sine would be 360. One bump up, one bump down. Takes us to 360 degrees. So there's one period, one full graph in a period of 360. For cos here, we go all the way down, all the way back up, and again, that would be 360. So our period for cos would be 360, or 2 pi if we're working in radians. When it comes to tan, all the way up, then all the way down, all the way up, this is happening only in 180. So 180 degrees or pi radians would be our full period for tan. So your period depends on what it is that you're looking at. So coming back to cos, we are working with the first 360 degrees. So we've said we have all silver tea cups, and it's all about who is positive. Okay, so from 0 to 90, from 0 to pi over 2, all our trig functions are positive, and that's wonderful. From 90 to 180, or pi over 2 to pi, only sine is positive. From 180 to 270, from pi to 3 pi over 2, only tan is positive. Then from 270 up to 360 again, so full rotation. So 3 pi over 2 all the way to 2 pi, only cos is positive. So this first quadrant is so important, okay, and he's our A, and this is where we calculate what we call PV, which stands for principal value. So if you can calculate your angle, okay, the answer to your equation that falls in this quadrant, then you can actually calculate all of them, because we can relate everything back to PV, our principal value. So if we're working in degrees, let's say, then for this quadrant, for S, if we wanted an answer in here, we would say, well, we want 180 minus PV. If we wanted an answer here, we would call it calculated by 180 plus PV. And if we wanted an answer here, it would be 360 minus PV. So for thoroughness, if we're working in radians, PV is still from 0 to pi over 2. Then we would have pi minus PV in this quadrant, pi plus PV here, and here we would have 2 pi minus PV. Because remember, everything we do for trig is exactly the same. The methods stay the same for degrees and radians, it's just the units that we're working in. So here's our class diagram. I just want to take a little bit of a moment to explain and to show you, to demonstrate how we can get all these values and why it makes so much sense for these. So we're going to use each of our graphs in order to do this. So we are going to take the first 360 of sine. So one rotation of sine. Then we're going to use a cos, also 0 to 360, 0 to 2 pi. So one period of sine, one period of cos. And then for tan, we also need 0 to 360 because that's what cast works on. But that means that we're going to have two graphs because our period is only 180. So now we've got two tan graphs coming here. So y and x. So let us have a look and we can see. If we take 30, because 30 is nicely in 0 to 90, right? We're going to take 30 on each of our graphs. Not necessarily to scale, but there's an idea. Now, think about this sign. Remember, I just said on the previous sign draft that I drew that I wasn't so happy with my bump. Okay, now this bump is perfectly symmetrical. So if this is 30, this line here is going to be exactly 30 from 180. So this is 150. 180 minus 30. Same with our cos. We are exactly symmetrical. So this line here, if we do a mirror line down the middle, this line here is going to be exactly symmetrical, but from 360. So a distance of 30 from 360 would give us 330. Now if we go to tan, remember, we're repeating the same graph over and over again. So that line there, if we draw a same line here, this is going to be 30 from 180. So 180 plus 30 is 210. And then we start to see some magic. Because if we say sine of 30, make sure you calculate this in degrees, and you get a half. If you do sine of 150, you also get a half. So if you do inverse sine of a half, you're going to get 30 because you're in your principal value. And then if you do 180 minus 30, you're going to get 150. And look, we've picked up that second solution. So with cos, if you do cos of 30, you're going to get root 3 over 2. It's a special angle. Okay? If you do cos of 330, you're also going to go root 3 over 2. If you do inverse cos of root 3 over 2, you're going to get 30. But look where cos falls. Cos is positive here. 360 minus 30 is 330. So we can work in circles and backwards and forward, and it's just wonderful because it gives us this ability to find those solutions without having to draw 6 graphs and understand what's going on every time. So the last one, if you do tan of 30, you're going to get root 3 over 3. So there's absolutely no prizes for tan of 210 because we've said it's going to be the same thing again, root 3 over 3. If you do inverse tan of root 3 over 3, you're going to get 30 only. But tan is positive here, so 180 plus 30 is 210. So our cast can take us and get us all of those solutions, so both solutions within that 0 to 360, and then we can have a whole lot of fun and games after that. So how do we actually take this into solving equations? Okay, first off, we are going to look at types of equations, then we're going to pull that through. So our types of trig equation. At AS, you are dealing with 3 different types. Okay, you have your simple trig, which is very simply trig theta equals k. So there's trig here, it could be sine, it could be cos, it could be tan, okay? Trig is standing in for all 3 of them. But it's just something like sine theta equals a half, okay? Inverse sine, but that's only going to get us 1 solution as we've just seen. So then we have to take it further with cast. So our quadratic trig, told you quadratics were crucial. A, trig squared theta plus B, trig theta plus C equals 0. Okay, so instead of having x, we've got a sine x. Instead of having x squared, we've got sine squared x. But it works just the same as any other quadratic. You can factorize it. You could even use a formula on it if you absolutely had to, if you couldn't factorize it. Okay, but it responds in exactly the same way. And our last one is our transformed trig. So this would be an equation where you had trig a theta plus phi equals k. So there's things happening to your theta before you do the trig function. So sine of 2 theta. So you would do 2 times your angle, then you would do your sine. So this is a little different from your first initial trig because things are packed in there before you're doing your trig function. So you've got simple trig, quadratic trig, and transform trig, but they all boil down quite nicely to simple trig with just a few additions on. So what we're going to do now is we're going to look at what are the steps that I'm going to follow in order to solve a simple trig equation, and then how can I build that out to do a quadratic trig equation or a transform trig equation. So today we're just going to look at the steps for it, and then in another lesson next week and the week after actually, we're going to work through trig past paper questions, and we're going to see how these graphs and identities and equations all come into one question and how we then use our full understanding to solve the equations. So, solving that simple trig equation, we actually need more space. So this would be, for example, if we had something like sine x equals a half. Okay, and you might just say, oh no, but I just say sine to the minus 1/2 and I get x and that's it. And yeah, but you're stuck at IG. Okay, what we need to do is we need to take it outside of that. We're working now with an understanding of domain. So we would be solving simple trig from 0 to 360, for example, or from minus pi to pi. And we would have to find all of the solutions within that domain. So it's not quite as straightforward as just trig to the minus 1. So first step, we want to get to the point where we have trig theta equals k. So we're going to simplify to trig theta equals k. And what we're going to do here is we're going to have sine theta equals a half. We could have sine theta equals minus third. And we're going to note the sign of k. Next thing we're going to do is we're going to calculate our PV. But remember, PV fell in that first quadrant from 0 to 90. And the thing about that is that everything is positive. So we can't say that sine theta equals minus a half because it wouldn't fall in that 0 to 90. So what we're going to do in order to make sure we get our PV is we're going to work with the modulus of k. So we're going to say trig theta equals the modulus of k. So we're ensuring that we get our PV and then we can work with it. So theta is going to equal trig to the minus 1 of the modulus of k. And then theta is going to give us some sort of answer. And we're going to label this answer PV. Because the thing is, that answer for PV might not actually be an answer to the equation we are trying to solve. It might just be a stepping stone on the way there. Okay, but we need it because it's a very important stepping stone. So we label it PV and we carry on. We now draw a mini cast. Okay, now by mini cast, I mean all silver teacups, very little. Okay, it's just to make sure that you're in the right place and you can see what's going on. Okay, why do we do that? Now we go back to that first step where we noted the sign of k. Because it's the sign of k and the function we're using that's going to tell us where on this cast are we working. So you're going to use your sign of k plus function that you're using to determine your quadrants, the relevant quadrants. So for example, if we had sine x equals positive a half, well, we need answers where sine is positive. So we will be looking at the A quadrant, everybody's positive, and the S quadrant, sine is positive. If we had sine x is minus a half, then we'd want something different, because now we'd want, where is sine x giving us a minus answer? And that would be in T and C quadrants, because there, tan is positive, cos is positive, sine is negative in both of those. So we would be working in the bottom two quadrants. So your sine of the k plus which function you're working with, because of course it's going to change depending if you're sine, tan, or cos, because they're each positive in a different place. So that then helps you to determine your relevant quadrants. Once you've got your relevant quadrants, of course, now you can calculate. So, are you doing 180 plus? Are you doing pi minus? Are you doing 360 minus? Are you doing 2 pi minus? Remember, if you're working in radians, you're doing your whole question in radians. If you're working in degrees, you're doing a whole question in degrees. So your cost, you need to be comfortable with it in terms of degrees or in terms of radians, so that you can use either one. So you calculate the values for your relevant quadrants, but you don't do it blindly. You're going to keep an eye on your domain. Okay, because depending on how your domain is restricted, you may or may not need to calculate more or less answers. Okay, so if we're working from 0 to 360, 2 answers, fantastic. If we're only working from 0 to pi, ooh, now that's only half of it. Now we're only going to get 1 answer perhaps. Okay, so it's really important that you keep an eye on your domain as you're working through these calculations. Now the last one, once you calculated values, you don't just leave them in sort of a mess of working out. You actually take the time to state your final answers, because as you've seen, we've got answers that we're going past in order to get to the answers. So we want to be sure the examiner knows exactly, now I'm sure these are my workings, these are my final answers. So you're going to state your answers to the original equation clearly. Solutions. Theta equals blah, blah, blah. Finished. One time. Okay, so you want it to be really, really clear. Now time has flown by so fast, so we're just going to touch on the approach for quadratic and transformed, and then we'll take it further. We'll combine the theory in with actually doing the questions. Okay, so quadratic trig. Well, if you think about it, we can get a factorized quadratic and we'd end up with like sine x equals a half sine x equals minus a third. So for a quadratic trig, we're going to do some manipulations before we do this simple trig. Okay, so then we're going to get 2 simple trig answers and we're going to work that. For a transformed trig, in order to deal with that transformation that's so tied to our theta, we'd have to get rid of the trig first. So for transformed trig, our manipulations come after our simple trig solution. So the be-all and end-all of your existence when it comes to solving trig equations is this 6 steps for a simple trig. And then we're either going to play before if we have a quadratic, and we're going to play after if we have a transformed. And then we're going to get all the wonderful solutions to all the wonderful equations.